and make that available afterward. We also are going to have a Q&A session at the end of Alex's presentation. So if throughout the presentation you have questions, feel free to submit those through the Q&A box at the bottom of your screen. We ask that you use the Q&A box as opposed to the chat. Please use chat more for technical questions or anything that you don't want addressed in the Q&A session. We'll keep an eye on both, but we just want to make sure we don't miss anything. So please submit all questions to the Q&A box. With that, I'm going to hand things over to Katie Smith of the National Renewable Energy Lab to kick us off.
Great, thanks so much, Jackie. Hi, I'm Katie Smith, one of the prize administrators for the Geothermal Lithium Extraction Prize, which is sponsored by the Department of Energy's Geothermal Technologies Office. I'm happy to introduce our speaker today for this webinar, Alex Grant. Alex is a principal at Jade Cove Partners. He's also a Forbes 30 Under 30 honoree in energy for 2021 and a research affiliate at the Lawrence Berkeley National Laboratory. Alex is a partner at Minviro, where he helps build environmental impact models of lithium-ion battery supply chain processes, as well as being a technology innovation advisor at Zelandes, a lithium brine field services company with operations in Argentina, Bolivia, and Chile. Alex is the co-founder of Lilac Solutions, a Silicon Valley lithium extraction technology company funded by Bill Gates' Breakthrough Energy Ventures. Alex has an MS from Northwestern University in chemical engineering and a bachelor's of engineering from McGill University in chemical engineering and philosophy. I'm so happy to have Alex here with us today. Thanks for joining us.
Thanks, Katie. Thank you for the introduction. Yeah, it's a pleasure to be here. Thanks to the DOE and NREL for inviting me to chat again with you all on geothermal lithium. So I put together a couple slides today to move towards answering this question that a lot of people ask, which is there enough lithium to make all the batteries? The answer is certainly. The better question is, well, how will we do it? Because there are many different opportunities to do so, and geothermal lithium is just one of those. So really quickly, I am a kind of technology consultant based in San Francisco, working on projects all around the world for both lithium projects in development, technology companies, investors, governments, and all different types of stakeholders who are interested in building new lithium supply projects that leverage new technology with lower environmental impacts compared to legacy alternatives. And part of what I do with my time is to publish research on these topics. So on my website, there's a research page where I've published a significant amount of information on some of the things that I think are true, interesting, and important to the energy transition with respect to lithium. So lots of free open content there if you want to go take a look later. So the grand challenge that I and many others are focused on and interested in is to figure out how to make 8 times more lithium from natural resources in 2030 than we do today. This growth in demand is driven by the growth in lithium-ion batteries used for electric vehicles, and it's pretty much set in stone at this point. So everyone's pretty confident that this is the technology platform that decarbonizes transport. So this growth in demand is pretty much guaranteed at this point, it's going to be a very interesting kind of scramble to build new operations that will make these lithium chemicals. So 85% of that lithium supply in 2030 doesn't exist yet. So there's tremendous kind of phase space to do new and different things that are ideally better than the way that we make lithium chemicals historically. There's kind of a headwind to that though. So as we start expanding into different types of lithium natural resources with lower grades and higher levels of impurities, they become harder to process. So it requires more energy and more reagents to extract, concentrate, and purify the lithium to make lithium chemicals that go into the cathode of lithium-ion batteries. And there's a concept that I like to refer to kind of articulate this challenge. And it's the idea of the mineralogical barrier. So if you plot a concentration of lithium in a resource, whether it's a brine or a mineral or whatever it may be, versus the amount of lithium in that resource, or any commodity or product, really, you'll see a graph that kind of looks like this. So historically, people first developed the absolute highest grade, easiest to find, easiest to process resources. In the lithium context, you might contemplate that that's something like the Salar de Atacama in Chile, which has very high concentration and relatively low impurity levels, and that brine is processed very, very straightforwardly. So there's kind of a set of technologies, legacy technologies, to process those legacy high grade, high purity resources. Those technologies don't necessarily scale to lower grade, higher impurity resources. So there are plenty of brine resources that cannot be processed exactly the same way as the Atacama. And in fact, every single brine resource is different, so they're all processed a bit differently. But really the point to take home here is that if we need to lower the grade of the resources we process, which we truly really do need to if we're going to expand lithium production by 8x, then we're going to need new technology to do that, which includes geothermal lithium, it includes sedimentary clay resources, it includes a number of different things. So where could this lithium come from? So I like to break down lithium natural resources into 3 families. The first are brines, which are very high salt content waters that are formed in closed basins in mountainous areas like the Western United States, the Lithium Triangle in South America, Chile, Argentina, and Bolivia, Western China, and a couple other locations. Those are unconfined aquifers, so they're very shallow, and they're exposed to air some of the time. And that's kind of different from confined aquifer deep brines like geothermal and oil field brines. And I'll talk a little bit about that in a minute. Pegmatite resources are formed from lava cooling very slowly in kind of volcanic processes. So they're formed millions and millions and millions of years ago in some cases. And they look more like kind of hard, white or clear crystals instead of salty water. So really quite different. And then there's a kind of intermediate family of resources called sedimentary resources that includes clays. They're sometimes all grouped together as clays, but they're not all clays. They are also solid, like pegmatite minerals. However, they contain the lithium in a different way in the mineral structure, so they're a bit easier. It's a bit easier to get the lithium out. So that kind of affects the way that they're processed into lithium chemicals as well. So today, all of the lithium production comes from brines and pegmatites, and only a fraction of the types of brines and pegmatites. And in the future, we're going to expand to a lot of the rest of these things. So just to give you a flavor of what I mean by a brine. A brine is just a salty water found in nature, right? There is no standard brine chemistry. So the variety of geochemistries possible for a brine is quite vast. All different lithium concentrations. Some produce potassium as well, such as the Atacama. The Atacama has very high potassium concentration. I mean, it was originally developed for potash production. Some contain a lot of magnesium and sulfate, which poses problems for conventional processing, since lithium can be lost to co-crystallization of impurity salts with those two. They contain different levels of calcium depending on the geology that contains the brine. So the brine is found within pore spaces of rocks and dirt. It's not found in like a big underground cavern or anything like this. So I guess kind of a takeaway from this table is that after the impurity to lithium ratio of a brine and after the grade of a brine, well, after an impurity ratio goes above a certain threshold and after the grade of a brine goes below a certain threshold, there's kind of a transition from pure evaporative processing. So these are the evaporation ponds you've seen potentially in Chile and Argentina, where brine is pumped in a pond and water is evaporated and salts are crystallized out of that brine slowly over a couple months. There's a transition towards using direct lithium extraction technologies, which I'll talk a bit about today, because it would just be too expensive and take up too much land to process low-grade, high-impurity brines using pure evaporation. And just to kind of drive that point home, lithium brines come in many different flavors. I like to break them down by thermodynamics and geochemistry. So geothermal brines are obviously high temperature and perhaps a little bit less obviously, usually high pressure. And that high temperature and that high pressure leads to higher concentrations of different things dissolving into the brine, like calcium, for example, from limestone. And it also results in typically slightly lower pH and lower oxygen reduction potential, which is kind of a proxy for oxygen content. Here I have kind of a really, high level rough demarcation between geothermal, oil field, and solar brines based on my experience working with the different types of brines. And I think it's interesting and kind of humbling to realize that almost all historic lithium production from brines comes from kind of that little box on the left. So shallow, low temperature, not super high pressurized brines that exhibit a certain kind of geochemistry, certain calcium content, certain grades of lithium in certain places, et cetera. And there, we've developed kind of a toolbox for processing those types of brines. And only now are we developing new tools to put in that toolbox to process brines from the rest of that, kind of phase of temperature, pressure, pH, and ORP. Minerals are solid resources, like I mentioned in a couple slides back. And there are many different types of lithium minerals. I break them up generally between pegmatites and sedimentary or evaporitic minerals. The most common pegmatites that are being developed commercially today are spodumene and micas like lepidolite and zinnwaldite. Whereas on the sedimentary side, most of the sedimentary projects that you may have heard of, such as the clay projects in Western United States, are usually called hectorite, though hectorite technically doesn't exist. It is a mineral that is described as questionable by the International Mineralogical Association. So everyone calls their sedimentary mineral hectorite, but it isn't actually like a real mineral, which is kind of interesting. So a lot of the projects developing these clays across the Western United States don't even really know what the mineral is, which is kind of hilarious. But hey, if you throw acid on it and lithium comes out, that's kind of all you really need, I guess. And then there's a couple other kind of unique and fringe minerals like yadarite and zabuyelite as well that are being developed. So the mineral space is super interesting. The composition of all these minerals is different, and the way you process them is also different, depending on the exact composition of minerals you have in a mineral deposit. So to kind of like wrap all this together, depending on the type of resource you have and depending on the peculiarities of that resource, different processing technologies and different pathways are required to make lithium chemicals from them. So to go from a natural resource all the way to something that would go in a cathode, there's a number of different steps, and every single deposit requires different tweaks of how those steps are implemented. I mentioned earlier that I believe that there's plenty of lithium to go around to make all the batteries. If you look at the ocean, which is, you could see it as a brine containing 0.2 milligrams per liter of lithium, which is, of course, 2 to 3 orders of magnitude lower than continental brines in grade. It's very low grade, but the ocean is so massive that it contains orders of magnitude more lithium than we could ever possibly want to use. So if someone was ever to develop a direct lithium extraction technology to make lithium concentrates from the ocean, that would be fabulous. It will probably be quite expensive if it ever does happen, because you have to move so much fluid in order to make a certain amount of lithium. But it would be pretty compelling. So until then, we have to deal with continental resources, and we have to ask some of the following questions. So how much lithium do we need, and how much do we need to make? From where? What type of resource? Whether it's a mineral or brine. in what jurisdictions. So, what state in Argentina with the best mining laws, using what kind of processing and extraction technologies, how much does it cost to build and operate, what are the environmental impacts of making the lithium chemical in that place from that resource, and what kind of lithium chemicals do you want to make, whether it's lithium carbonate or lithium hydroxide or chloride to make lithium metal or whatever it may be. And there's an eighth question that I should add at some point, which is how much time will it take to build a new extraction operation? And that is also different for different types of resources and also very important. So in order to process these lower grade, higher impurity resources that we really must do in order to grow lithium supply significantly in the 2020s, the future will really necessarily have to look quite different from the past. So, conventional technologies are not going to be able to satisfy all of our demand in the 2020s. That's kind of undisputable. Enter DLE. So I'm really fascinated by DLE. I've been involved with DLE technology development. I've worked on DLE-enabled projects, so resource projects, and I've spent a lot of time studying all of the different options for DLE. In general, a DLE technology is a technology that leverages a selective site on an engineered material to selectively remove lithium from a brine or any other lithium-containing solution without the need to remove the water and the other impurities from the brine. DLE has been used in Argentina by an American company for 2 decades, so it is actually not new. And in the last 10 years, it's been deployed on around 5 different brine projects in Qinghai in China. So in China over the last decade, there's been a tremendous kind of boom in activity in DLE, which is very exciting and promising for the rest of the world, since China's kind of 5 to 10 years ahead on battery supply chain development compared to us. So I just want to impress on you that the DLE is not brand new. This is not like a science fiction concept. People have been working on this for decades. Do DLE technologies need a bit of an upgrade to tackle those more challenging brines like geothermals? Yes. And is every single brine unique? Therefore, every single project with a process developed for that project unique? Yes. So by no means is there kind of an off-the-shelf approach that requires no technical work. That's definitely not the case. And developing a DLE process is hard. Definitely not not always the most straightforward, simple way to make lithium chemicals. There are other ways to make lithium chemicals with significant externalized impacts, like whether that's digging a pit or otherwise. But yeah, so DLE is not new. There are 3 types of DLE in general that are the main families of DLE technologies: adsorption, ion exchange, and solvent extraction. The American company Livent uses an adsorption technology in Argentina, and they have for the last 2 decades. And a couple adsorption technologies have been deployed in China in the last decade as well. A number of ion exchange technologies are being developed now and reaching relatively late stages of development. So that's very exciting. And a couple solvent extraction technologies have been developed and have tried to be commercialized, but haven't really had tremendous success to date. There are some other classes of technology, such as electrochemical lithium extraction approaches and kind of advanced nanofiltration approaches. I don't include them here because they are significantly less prospective, in my opinion, and I won't go into all the reasons why. But in terms of membrane processing, the issue is that a membrane does not upgrade the lithium in the permeate of the process. Therefore, it fails at a really crucial. It fails a really crucial kind of test for having high performance in DLE. But that's tangent. So just wanted to share this slide from Livent's 2020 sustainability report that came out about a month ago. They're actually talking very specifically about their extraction process and explaining it so that people understand that the way that they make lithium chemicals from their brine in Argentina is very different from the way that they make lithium chemicals in Chile at the Atacama, for example. And they actually use this information as part of their storytelling to customers and investors to essentially kind of win and have commercial success, really. So BMW signed a offtake contract with Livent a couple months ago, and like specifically mentioning their extraction technology in the press release, which I found fascinating. I thought it was kind of like the first DLE offtake, the first time someone promised to buy lithium chemicals because of the type of extraction process that was deployed. So Livent's technology is not the most advanced DLE technology. Well, I mean, it's the most commercially advanced, obviously, because it's been used for 2 decades, but it's not the most sophisticated, I would say. And it doesn't necessarily copy and paste to be deployed on a geothermal brine, for example. So significant kind of updates have been made to this type of technology and other types of technology in the last couple of years that go even further and kind of make even better promises around environmental impact. As I mentioned, I study these technologies, kind of all of the activity happening globally, and mostly gathering public information and curating it according to my kind of fundamental technical insights. I of course also have a lot of confidential information on a number of these technologies and projects, which I do not publish, and I don't share with others. But this is kind of a high level overview of my assessment. So this is just my view of kind of the information I've collected on different technological approaches to DLE. I'm tracking around 73 different technologies at the moment, all around the world. So that is really quite a high number. And a couple from TRL 6 to 8, which are kind of mini pilot and pilot scale development, including those at TRL 9, i.e. commercial scale. So this, I use this research to help projects in development and investors make decisions about what technology to use for their projects, and to really just develop a global perspective that helps me evaluate like what is true, what is real, what is important, and kind of cut through marketing fluff, for example. So this brings me to geothermal lithium. So I published an article about a year ago called Geothermal Lithium, the Final Frontier of Decarbonization. So kind of a dramatic title, but basically what I wanted to do in this article was to articulate the environmental performance value proposition of geothermal lithium products. So it's easy enough to go around telling people that your geothermal lithium is going to be green, clean, and sustainable, whatever have you. But I don't think that that's like a really professional sustainability communication strategy. I think that if you really want to communicate the environmental performance of a chemical product, for example, you need to quantify it, whether that's in CO2 emissions or land use change or water use or whatever it may be, whatever impact category and life cycle assessment you care about. Most people care about CO2 emissions for the most part. But yeah, so what we did was we had data from one geothermal lithium project in California and one in Germany at different stages of development. And about a year and a half ago or 2 years ago, we built life cycle assessment models of those projects. So these are real commercial projects. These are not academic curiosities. These people are actually trying to build chemical plants to sell lithium chemicals. And we calculated their CO2 emissions, their CO2 emission intensity from scope 1 to 3, so including their supply chains, which is critical. And we did find that they likely would have relatively low CO2 intensities of manufacturing lithium hydroxide from those geothermal brines. And that includes a offset credit for selling power as well, since the geothermal lithium concept is to bring brine up from deep underground, produce power or potentially district heating, and then take the lithium out. And they would also, of course, have very low physical footprint. So very, very little land would be required to make lithium chemicals this way compared to evaporation ponds, for example. Geothermal lithium is also not new. So DLE has been around for 20 to 30 years. Geothermal lithium has been around for around 10 years. Most of that activity has happened in Salton Sea area in Southern California. with some, very kind of notable projects that have progressed to kind of medium stages of development and failed. But now there's a couple different players down there trying to make it work, which I'm very excited about. I really hope they all succeed. But yeah, so Southern California has been kind of the mecca of geothermal lithium. Recently, in the last 5 years, there's been a lot of activity also in Germany and France. So there's a rift valley that goes kind of under the border of Germany and France called the Upper Rhine Valley, which kind of shares similar geology to the Salton Sea. A couple companies there have been working on geothermal lithium for the last couple of years, including one which has recently published updated life cycle assessment results, which I'm going to share a little snippet of. And then beyond those two, I'm not aware of any really significant geothermal lithium brine development activity. Most of the other dots on this map are kind of more science experiments than real projects. And part of the reason why is because the grade is a lot lower. So if a brine is close to the ocean, then I'm not a geologist, but my understanding is that that brine is often composed, at least partially, from ocean water originally, meaning a very low lithium concentration brine is kind of, or a very low lithium concentration ocean water is kind of used to make that brine to some extent. So that's why those brines typically have lower grade and they're very small. They're not found in the same kind of rift valley that the Salton Sea and Upper Rhine Valley have. So there has been some activity in Japan, New Zealand, and the UK, and a little bit in Iceland as well. But it's not really commercially relevant the same way that France, Germany, and the US are. And just to be clear, just so I put an asterisk beside all of this, no geothermal lithium chemicals exist at commercial scale yet, and never have. So these are all in development phase, and there's still a lot of work to do to make it successful. So it's definitely, even for the most prospective projects, it's not a slam dunk. So I wanted to share a case study from a project that I've been associated with for the last 2 years called Vulcan Energy Resources. So it's a 2-year-old company developing a geothermal lithium project in the Upper Rhine Valley in Germany. And Vulcan hired Minviro, which is a life cycle assessment practitioner that I am very closely involved with in London, to build LCA models on their process at their scoping study stage, which is a very early stage of development. I actually showed the number in a couple slides before, and then more recently at the pre-feasibility study stage. And they recently just published these results last week. So these results are based on having done more test work and done kind of more detailed engineering for their geothermal lithium product in Germany. And in the study, we went through and we calculated the CO2 emissions for their product again, kind of estimated. In the first study, with the power offset, the estimated CO2 emissions of the lithium hydroxide was around -5 kilos of CO2 per kilo of lithium hydroxide monohydrate. In the updated version, it's -3. So they've kind of lost a little bit of that CO2 mitigation opportunity as they did more process development and got more data and learned more about what would actually be required. So we'll see how that evolves the next time they do an LCA on their full feasibility study, probably in the next year or two. But kind of power offset credit, like regardless of if you accept this credit in their carbon accounting, or whatever other qualifications you would add, it still has the potential to be a very low environmental impact product, and we articulated that with LCA. So there's a lot more information on the internet if you want to go look it up. But Vulcan has done pretty good work using prospective LCA to remove environmental impacts before their project is built. And I think all projects should be using LCA in a similar way because it's really powerful. So I'll hand it over to the DOE to tell you a little bit more about the Geothermal Lithium Extraction Prize, and then yeah, perhaps close after that. So Katie, do you want to take these two?
Yeah, great. Thanks so much, Alex. That was a fascinating presentation, and I took so many notes. So unless we get questions from the audience, I have a bunch of questions for you once we talk about these. But we did want to mention today the American-made Geothermal Lithium Extraction Prize. This is a prize that is currently running and being sponsored by the U.S. Department of Energy's Geothermal Technologies Office. The prize is designed to de-risk and increase market viability for direct lithium extraction from geothermal brines. So I think many of you are familiar with this prize already. It is a 3-phase prize. And the first phase submissions are due September 2nd. So there's still time to participate and get those entries in. Between the 3 phases, there are over $4 million in prize money. So lots of money out there to be won, which is really exciting. We did recently update the eligibility rules for this prize. So small businesses are now allowed to participate, assuming that they are partnered with an accredited educational institution here in the US. So we're really looking forward to seeing some of those small businesses further build their relationships with colleges and universities that are near them to come up with some great ideas that will hopefully advance geothermal lithium direct lithium extraction. And like Alex said, direct lithium extraction could be a game-changing extraction method. We could get 10 times the current US lithium demand from California's Salton Sea's known geothermal area alone. So there's so much potential, and we're really looking forward to seeing all of the solutions that the teams come up with. Alex, can we have the next slide, please? Great. And then because we do have a bit of an academic audience on this call, we did want to mention the 2020 Geothermal Collegiate Competition. This prize was it was announced in June and the rules were posted just last week. This is even bigger and more ambitious than our previous collegiate competitions. This year, the competition will take place over a full academic year, and teams are being asked to identify a community or campus site for a direct use or district use geothermal system. We have expanded some of the work that needs to be done within there. So there'll be different modules that teams can choose to compete in and participate in based on the interests of their teammates. And we're also offering bigger cash prizes and in-person community engagement events with the winning teams. So we're really excited about this prize as well. And we encourage everyone here to check out the HeroX website, sign up for information or join a team.
Cool. Go do that. Yeah, I guess so. Just to wrap up, there's plenty of lithium in the world. Geothermal lithium is a super interesting, exciting way to make lithium chemicals. I wish all of the competitors in the extraction prize good luck. It's going to be very interesting to see what you come up with. Yeah, perhaps there could be a step change off the wall, kind of new technical ideas that could add a lot of value here. Or at least some kind of tweaks that could also be useful. So yeah, excited to see what you come up with. And there's lots of content on my website if you want to learn more about lithium in general. And I'm very easy to reach. So feel free to ping me by email if you ever want to chat about this stuff.
Great, thanks so much, Alex. So we have a couple questions that have come in. So let's get started with those. So it looks like our first question is, would concentrating geothermal brine assist with costs associated for direct lithium extraction? So for example, extracting the water before.
Theoretically, yes. However, it's already such low grade that if you wanted to bump up the grade by 2x, you would be removing an extraordinary amount of water, which would likely require an extraordinary amount of energy, probably more energy than the plant produces. So that is why I think all of the commercial projects in development focused on geothermal lithium are not proposing to do that, because that energy is needed elsewhere.
Great, thanks. And Alex, can you elaborate on the reasons that make electrochemical and nanofiltration methods less promising for DLE?
Electrochemical processes on low-grade brines would result in very, very high capital expense, most likely, because it would be a very novel technology, not implemented on a low-grade brine before for lithium extraction, as far as I know. You know, someone else might be aware of some projects somewhere that I've never heard of, but it has been used on brine concentrates with higher grades, but I would be concerned about the cost of membranes to enable such a project, and in some cases the price of power is actually relatively high depending on where you are. And sometimes it's more valuable to sell that power instead of use it. So that's why I am not optimistic about electrochemical lithium extraction, especially from geothermal brines. And when it comes to kind of more sophisticated nanofiltration type extraction, there are a couple different technology solutions in development focused on that. None of them particularly serious, in my opinion. Really, the issue with membrane processing on natural brines is that they don't upgrade the lithium. So if you're starting with 200 milligrams per liter and you get less than 200 milligrams per liter out, that is not desirable. You really want to see it concentrated at least 3, 4, 5x or more after a DLE process. So membranes are used in all DLE processes, but not for, well, they're used in all DLE flow sheets, I should say, but they are very likely not going to be used for lithium separation and purification from a natural brine.
Great, thanks, Alex. So we have one more question that's come in here for you. And the question says, it sounds like all serious DLE technologies using geothermal brine today are trying to use the brine directly following the geothermal plant without any concentration of the brine to start. Is that correct? And if so, is the issue with pre-concentration that the full water volume is not available for reinjection to the geothermal process?
Yeah, so I kind of half answered that question already, but I would add that in some confined deep aquifers like geothermal oil field wells, you actually need to put in a certain amount of fluid to keep brine flowing. So if you pump out more fluid than you put back in, you can depressurize an aquifer, and you would increase the amount of energy required to actually put to take lithium out, because you would be pumping against a higher or a lower pressure, I guess. So there's a number of reasons why no one is contemplating significantly changing the volume of water in the brine in geothermal lithium projects.
Okay, great. And then we just had another question come in, Alex. So with DLE technologies that you're very familiar with, do you have a guess as to what the milligrams per liter concentrations are likely to be commercially viable before 2030?
Yeah, so I won't comment on specific technologies
Right.
or companies, but just looking at DLE globally, like there have been folks pursuing brines containing lithium in the tens of milligrams per liter. Probably the most serious effort to process brines below 100 milligrams per liter is, I'd say, E3 Metals in Alberta. I think their average brine concentration is like 75 milligrams per liter, something like this. So it's really low. I mean, that's an order of magnitude lower than legacy brines, right? Which carries challenges. So it's probably not the easiest brine in the world to make lithium chemicals from, but take this analysis for a grain of salt. But like, I just don't think they would have kind of gotten so far if it was impossible to take lithium out of a brine like that. So I believe it's possible. Will the cost be $4,000 per ton LCE or $8,000 per ton LCE? Time will tell. we'll have to see what kind of process development they end up doing, and kind of what the contents of technical reports that they publish in the future.
Great. And then, so Alex, we have some questions coming in about some of the waste products that are common in DLE processes. Are you able to speak to any of those? What we could try and reduce on that side, et cetera?
Yeah, so the magic of DLE is that it takes lithium selectively out of a brine and leaves everything else, right? So it doesn't produce a bunch of salt waste products like evaporative processes do, for example. So if you're comparing to other kind of legacy processes, it's significantly less. Some DLE processes have waste products. I mean, all do to some extent. There's no such thing as a 100% pure concentrate out of a DLE process. So if there's calcium or magnesium or sodium or potassium in the concentrate, it needs to be removed to make lithium chemicals. That can end up being a waste product that doesn't necessarily end up back in the brine. But kind of most mature DLE technologies do not involve really exotic waste products like exotic phosphates or long chain hydrocarbon solvents or anything like this. Those kind of approaches have not had tremendous success and progress broadly. So I don't expect most DLE processes to produce really problematic large quantities of toxic waste or anything like this. But it's a very project specific and resource specific question. So, if there's something in the brine that is toxic and also causes issues for DLE and it needs to be removed, then that could end up as a waste product, and that needs to be handled carefully and professionally.
Wonderful, thanks, Alex. And then how do you think that the impurity levels of lithium from DLE compare to that of evaporative and hard rock extractions?
Impurity levels of DLE compared to evaporative and hard rock. So the major kind of the overall theme is that DLE can be used, or is proposed to be able to be used, for brines containing higher levels of impurities. You can't really compare the impurities in a spodumene concentrate to impurities in a geothermal brine or any other brine you process with DLE. It's totally different kind of process logic. But the point is that DLE can be deployed on lower grade, higher impurity brines.
Okay. Sorry, we just had a bunch of questions come in at the same time. So Alex, we do have someone asking if the DLE techniques put the water back into the geothermal reservoir to maintain pressure of the source. And I think you covered that a little bit already earlier.
Yeah. Depends on the hydrogeology. Yeah, sometimes it's needed, sometimes it's not needed.
Great. So we've talked a lot today about DLE technologies for the first step of lithium extraction. Do you have any comments on the approaches to convert extracted lithium into lithium salts?
Mm-hmm. Yeah, so once a concentrate is made, there's a number of different ways to make lithium chemicals from it. I'm aware of a couple of different approaches for kind of novel techniques for making hydroxide and carbonate from chloride and sulfate concentrates. The thing is, once you have that concentrate, there's already commercially mature and low risk ways to make lithium chemicals from them. So the kind of the lift and the added value of processing the concentrate from a very low grade, high impurity natural resource is really much more significant than processing that concentrate into a lithium chemical. Since you literally can just use relatively conventional off-the-shelf techniques for doing that. Today. Are there better ways to do it? Of course, right? But it's not like a 0 or 1 kind of situation that DLE offers. Like DLE makes salt and sea brine, a lithium resource or not. And there's no downstream technology that offers that same kind of, toggling on and off of the value of the entire, geothermal lithium idea.
Okay, great. Thanks, Alex. We did have one question come in through the chat that Alex, I'll actually take. It's asking who will review the applications and should teams be worried about their IPs. We do have a group of industry and national lab experts who will be the expert reviewers and judges for this competition. All of our judges and reviewers do sign NDAs and confidentiality agreements. So, you don't need to worry about your IP. Please do make sure that you read the official rules with regards to marking your submissions as confidential if necessary. And it's all outlined in the rules document, which can be found on the HeroX site, which Jackie posted in the chat a little bit earlier. So, Alex, any closing comments for us today?
David asked another question. Are there any potential lithium resources outside of those already being developed that intrigue you as possible application of DLE? I've seen some activity focused on using DLE in sedimentary clay processing that I think is prospective. So we'll have to see where that goes. Yeah. So to answer the question, yes, I think that beyond just weird brines like geothermal brines, DLE could be helpful. In fact, actually, I saw in a sustainability report from a Chinese lithium company a couple months ago that they're using an absorption process in a recycling stream already. So I actually found that really interesting. I have no idea what exactly they're doing, but DLE is being implemented on waste streams just to increase overall lithium recovery. That's already happening today. So we won't try to explain it any more than that because I don't really know that much more about what's happening in China, especially. Yeah, so yeah, definitely has other kind of applications.
Wonderful. Thanks, Alex. So I think that's about it for us today. Alex, thank you so much for being here and having this great discussion with all of us. So much interesting information about DLE, and I hope that all of our viewers enjoyed the talk. And for more information regarding the Geothermal Lithium Extraction Prize, please check out the HeroX website, which Jackie posted earlier, and we will also be posting a recording of this webinar on that site as well as soon as we have time to process and edit it. So thank you all so much and have a wonderful afternoon.